Welcome to video 6 for the summer homework packet. This is the answer key for problems 14, 15, and 16. Alright, solving 14a, what we have is a quadratic inequality, which looks x squared 2x minus 3 is less than or equal to 0. And basically we're asking, when is this curve below the 0 line? That's one way to think about it graphically. So in order to find when it's below the 0 line, we want to find where it equals 0. So first we'll start by finding where it equals 0. And we can factor this to x plus 3 times x minus 1 and use the zero product property to see that we have solutions of negative 3 and 1. Then what we want to do is test the intervals between and outside of negative 3 and 1. So if I tested the value of 0 and I plug that into the equation, I'm going to get an answer of negative 3. And negative 3 is less than 0. So this is a true statement. If I test, we'll say 5 into the equation, we're going to get 25 minus 25 plus 10 is 35, minus 3 is 32. So that is false. Similarly, we'll test negative 5, because that's below negative 3. And we get 25 minus 10 is 15, minus 3 is 12. And that's also greater than 0, so that's a false statement. So our only solution is between negative 3 and 1. And since we include our zeros, we want to include them down here. So let's round that out by being inclusive. And if we wanted to write it all in set builder notation, we could say all x such that. But generally this will work, or if you want to write it as interval notation, negative 3, comma 1 with hard brackets. Okay, 14b, we're dealing with a rational function, 2x minus 1 over 3x minus 2. And we want to know when is that less than or equal to 1. And right away when I see a rational function, I want to start to consider things like vertical asymptotes. Are there any vertical asymptotes or holes? And if I subtract or set this equal to 0, I find that there's a vertical asymptote at x equals 2/3. And that's an important feature. The other important thing I want to look for is when is this statement equal to one another. So let's go ahead and solve this. 2x minus 1 is over 3x minus 2 is equal to 1. And we can multiply the 3x minus 2 across and then solve for x. Add the 2, we get 1. Subtract the 2x, we get x. X equals 1. So there are our test values, there, and there, or just the two of those. So again, we'll set up a number line like we did before, and we've got 2/3, and we've got 1, and let's test some values. So a number less than 2/3 is 0, so if I plug 0 into the equation, I'm going to get 1/2, which is less than 1, so that's true. If I plug, we'll go with 5 into the equation, we'll get 9 over 15 minus 2 is 9/13. That's less than 1, so that's also true. And then a little bit harder here, let's pick a number greater than 2/3, maybe 0.8. And I might turn to the calculator for this, but we get 0.8 times 2 is 1.6 minus 1. That's 0.6 over 2.4, 0.4. That value, 0.6 over 0.4, is actually bigger than 1, so that statement is false. So our solution set would be from negative infinity to 2/3 in union with 1 to infinity. And since we are including where it's equal, we want to actually make these hard brackets because we include those values. If we turn to a calculator to look at what this looks like on the graphing screen, we would find that at 2/3 we have a vertical asymptote, and then there's a horizontal asymptote as well, but that value of 1 is right about here. So we've got from negative infinity to 2/3 is underneath that red line, and then from 1 to infinity we're underneath that red line. So this occurs at 1. All right, let's look at the next one. All right, 14C, we're looking at another quadratic, and we're wanting to know when is that quadratic above the curve. And looking at this quadratic, I can try to factor it, but there actually is no way to factor this. So in solving the quadratic equation when is at 0 to find our test values, I'm going to go ahead and use the quadratic formula. So we're going to do negative b plus or minus the square root of b squared minus 4ac all over 2a, and we find that we have a complex number. 1 minus 4 is negative 3. And because of that, because of this fact that our root is complex, or our two roots are complex, we know that it never touches the axis. So then the question is, does the curve open up or down? And because the leading polynomial is positive, we know it opens up. Not the leading polynomial, the leading coefficient is positive. It opens up, so the curve opens up and never crosses the axis. There's no spots where it crosses the axis down here. Therefore, that curve is always above 0. So our solution is negative infinity to infinity. Are we looking at cell formation, or are we looking at distant galaxies? All right, in problem 15, we're looking at absolute value problems. So, quick refresher here. The absolute value can be thought of as a piecewise function defined as x when x is positive, or defined as the opposite of x when x is less than 0. So in other words, if we had 7 in here, we would be in the top field, and the answer would be 7. But if we had negative 7 in here, we would be in the bottom field, so negative 7 makes it positive. And keeping that definition in mind will be very useful in calculus and useful in solving these problems. So if you don't have that written down, write it down. Applying it to the first problem. Negative x plus 4, all in the absolute value, is less than or equal to 1. So in this case, we have two conditions. We either have the condition negative x plus 4 is less than or equal to 1, or we have the condition the opposite of negative x plus 4 is less than or equal to 1. So one of those two conditions can exist. If we go about solving this out, we're going to subtract 4 from the left-hand side and the right-hand side, and look at that, and then we'll multiply the negative through, and remember, when multiplying a negative, the inequality turns. So on the right-hand equation, we'll multiply the negative first, and the inequality will turn directions, and then we will take 4 away from both sides, and then finally we'll multiply the negative through, turning the inequality, and we get either x is greater than 3 or less than 5, and that winds up becoming a conjunction. So there's your solution. Graphing this on a grapher, you would probably find very similar results, where what we have is something like this. From 3 to 5, we are less than or equal to 1. Most important is the analytical approach, which is what we did here. Second to that is being able to use a grapher to help us confirm our results. Okay, 15b, another pretty straightforward absolute value problem. The absolute value of 5x minus 2 is equal to 8. So we'll first split it into its two parts. In the instance where the absolute value is greater than 0, we have this. And in the instance where the absolute value is less than 0, we have this. So going about solving this, we get 5x equals 10, x equals 2. And let's flip the sign to the right-hand side. 5x equals negative 6, x equals negative 6/5. So we get two answers. X equals 2 and x equals negative 6/5. Though technically x can't be both, so it's one or the other. Small distinction that I wouldn't mark anyone down on. Okay, 15c, we have the absolute value of 2x plus 1, and we're setting that equal to x plus 3. And just like all of the absolute value problems, we're going to set up two separate problems and solve them independent of one another to arrive at our solution. So first off, we'll solve the left-hand one. We're going to subtract the x to this side and get x. We'll subtract the 1 to this side and get 2. X equals 2 is one solution. Let's distribute the negative here. Negative 2x minus 1 equals x plus 3. Then we'll add 2x to get 1 plus 2 is 3x. And we'll subtract the 3 across to get negative 4. And then solve for the x. There we go. X equals 2 or x equals negative 4/3. The Great Red Spot on Jupiter is roughly the size of 3 Earths. It's a huge storm brewing on the surface of Jupiter. 3 Earths. 1, 2, 3 Earths. Alright, problem 16 is about lines and line equations. And the first one we're asked to do is find the line through negative 1, 3, and 2, negative 4. So the first thing I'm going to do is find the slope, and that's y2 minus y1 over x2 minus x1, and that gives me a slope of negative 7/3. So the equation of the line would be y minus y1 equals negative 7/3 times x minus x1. And that minus minus could become a plus if we wanted to. You could also use the second point as well. Y minus negative 4 equals negative 7/3 times x minus 2. Either one of these works, and that's the point-slope form. So some important formulas to remember. Slope is y2 minus y1 over x2 minus x1. And the point-slope form, the one we will use most frequently in calculus, is y minus y1 equals m times x minus x1. A slightly modified form, which sometimes I'll use, is called the Taylor form, and that's just going to be taking the y1 and moving it to the right-hand side. So this one and this one are the two that I'll most frequently use in calculus. Alright, 16b, we're going through negative 1, 2, and we are perpendicular to the line 2x minus 3y plus 5 equals 0. So we need to find the slope of this line. So the easiest way that I find slope is solving it for y. Negative 3y is equal to negative 2x minus 5. Y is 2/3 x plus 5/3. Now that we know the slope of this line is 2/3, the perpendicular slope is going to be the opposite reciprocal. So now we want an equation that has that two pieces. And using point slope form, y minus y1 equals m times x minus x1. Or if we did it in Taylor form, 2 minus 3/2 times x plus 1. And Taylor form is really nice for the people who are going on to Calculus BC, and it has application to one of the skills that we'll learn in Calculus AB. All right, 16c, we're looking for an equation that goes through the point 2, 3, and the midpoint of negative 1, 4, and 3, 2. So real quick, let's find the midpoint. The midpoint is the average of the x. So 3 plus negative 1 is 2, and we divide that by 2, and we get 1. And then the average of the y values, 4 and 2, is 6 divided by 2 is 3. So there's our equation, or sorry, our point, second point. This is the midpoint of those two coordinates. So we want the line through those two values. So first off, we'll find our slope. M is y1 minus y2 over x1 minus x2. And we get a slope of 0. Oh boy, we have a zero-sloped line. A zero-sloped line is that horizontal or vertical? We have a 0 rise, so that means it's a horizontal line, which means our equation is going to be y equals a number, and in this case 3. But if we wanted to go through the process of using point slope form, y minus 3 is equal to 0 times x minus 2. And the 0 cancels, and y minus 3 equals 0, y equals 3. So whichever approach you want to take, I think plugging it in like that would probably be easiest because it's the most common way. And then if you wanted to simplify it, that would be awesome. Okay, looks like we got a little typo here in problem number 16. Rather than going to part D, we repeated part A. So 16A2, find the intersection of the line 3x minus y minus 7 equals 0 and x plus 5y plus 3 equals 0. And there's a variety of ways we can do this. We can use the equal values method. We could graph them. Basically, we want to know what x and y values make both of these statements true. And I think that I'm a big fan of using elimination. So I'm going to go ahead and write both of these equations on top of one another. And use elimination. So first off, my bottom equation needs to have the same variable coefficient. So either I need to multiply the bottom one by 3, or I need to multiply the top one by 5. So I'm going to multiply the bottom one by 3 and rewrite the equation. 3x plus 15y plus 9 is equal to 0. And then I will subtract the equations to eliminate them. 3 minus 3 is 0. Negative 1 minus 15 is negative 16y. And then negative 7 minus 9 is negative 16. This equals 0. And we find that y occurs at, add the 16, divided y is at negative 1. So there's our y coordinate, and then we want to find the x coordinate, and we will do that by, let's substitute it in. X plus 5 times negative 1 plus 3 is equal to 0. And we get x minus 5 plus 3, x minus 2 equals 0, x equals 2. So our intersection point occurs at 2, negative 1. And just to be safe, we will check our answer by substituting it into this equation. So 3 times 2 is 6, minus negative 1 is 7, 7 minus 7 is 0. So that works out. Okay, finally, the last one of 16, 16b2, or 16e, I guess. Shade the region in the plane described by the inequalities 3x minus y minus 7 is less than 0, and x plus 5y plus 3 is greater than or equal to 0. So first off, let's write this as in slope-intercept form, because I find that easiest to graph. So the top equation becomes y is greater than 3x minus 7. And the bottom equation, we get 5y is greater than or equal to negative x plus 3. Y is greater than or equal to negative 1/5 x plus 3/5. Negative 1/5 x plus 3/5. Alright, so now that we have our two equations, we can graph those equations. And I'm being very loose here, just sketching it out. 3x minus 7, so 1, 2, 3, 4, 5, 6, 7. The y-intercept is at 7, and it has a slope of 3. So that's up 1, 2, 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1. And we can keep doing that, but let's just go ahead and dash in the line. And we do a dashed line because it is just less than, not less than or equals to. And we're going to shade the area less than that line, which would be the area below the line. Our second equation is has a y-intercept of 3/5 and a slope of negative 1/5. So this is going to be a very loose 1/5, but it's a very, very gradual slope like that. And we want to shade the area that is greater than that line. So we are going above it, which means our solution is just the quadrant or the portion that is double shaded. So this area in black is the only part that satisfies both equations. Stay curious, another video coming up shortly.